So guys, what we have here is a disc of mass m and radius r rolls down a slope inclined at 30 degrees. 30 degrees, no bother. Okay, the slope is rough enough to prevent slipping. All the motion is going to be caused by rotations. Okay, it's going to be a combination of both things though. It's going to be moving with linear kinetic energy while it's spinning at the same time. So it's going to have inertial energy and regular kinetic energy this time, because it's not just spinning on a point, it's moving and spinning at the same time. Okay, the disc travels from rest a distance of 120 meters down the slope. Show that the final linear velocity of the disc is 28 meters per second. Okay, so what we're going to start off with is we're going to say gain in kinetic energy equals loss in potential energy. Is everybody right with that? Gain in kinetic energy equals loss in potential energy. Right now your center of gravity is located a certain distance above the ground. When you reach the bottom of your journey, you treat that value as h equals 0, and you find out how much potential energy was transferred over to the kinetic. Okay, so there's two types of kinetic energy. There's a half mv squared, and then there's a half I omega squared, where omega is the circular velocity. Now you're talking about the circular velocity at the point of contact, because that's the circle you're rotating around. It's where it contacts the plane. Okay, so you're talking about that being your radius there, radius r. Okay, so it's the discs of mass m. So half mv squared, with v being its velocity going across, works absolutely perfectly. There's no hassle with the half mv squared. We got to work on the half I omega squared is what we got to work on. So it's a half mv squared. Now, what's the radius? What's the moment of inertia of a disc that's rotating perpendicular to the plane of the board from the center of the disc? Half mr squared. Okay, so it's going to be bracket a half mr squared. Okay, now w and v, not the most compatible lads going. Okay, so do we have a converter there at all? Any way of converting omega into v? V equals r omega. Omega equals v over r. We're going to convert omega squared into v squared over r squared. Okay, and then that in turn is going to equal, let me just drag all this up for a minute. There we go. And then we're going to have to sort out the drop in height. mg h. H is going to represent the drop in height this time. Okay, now to calculate the drop in height, what we're going to have to do is, how far do we actually roll down here? We go 120. So you're talking about 120 in this direction here. Okay, your potential energy is your vertical drop. Anybody tell me how to calculate what the vertical drop was? 120 sine 30. And in your solutions you'll see mg 120 sine 30. What is 120 sine 30? It's just 60. So that there is 60, a drop of 60. Now, r squared cancels with r squared, leaving a half mv squared plus a quarter mv squared equaling 60 mg. Extend the page downwards, cancel the m's. 3/4 v squared equals 60g. Multiply by 4, divide by 3. We're going to get 80g equals v squared. V equals root 80g. Okay, otherwise known as 28 meters per second when you convert g into 9.8. Exactly what we're asked to do right there. Okay, find the time taken to travel the 120 meters. How fast did we actually do this? Okay, good old UVAST, lads. UVAST. Our U value is 0. Our V value 28. Our S value 120. We got to find our T value, isn't it? So if we find the acceleration, we can then use the acceleration to find the time. So what we can say is phi squared equals u squared plus 2as. 28 squared equals 2 times 120, which is 240 a. What's 228 squared divided by 240? Let's go with an a value of 49 over 15. You can check that out for me in a second. Then we can do phi equals u plus at, where the phi value is 28, the u value is 0, the a value is 49 over 15, and the t value being t. T therefore equals 28 multiplied by 15 divided by 49, and that gets me a t value of 60 over 7. I'm going to pause it here for a minute. Quite some while now. Kinetic particles, yeah? Please pay attention. Okay, in kinetic particles, and I would have mentioned this in passing, the other week, is that, believe it or not, these pulleys, you always hear the description, smooth pulley, don't you? In the kinetic particle questions, yeah? This isn't actually rotating. So the central pulley now, I only learned this when I started doing inertia, okay, is that it's not actually rotating like you think. It's actually like the ice analogy. The string is slipping over the side like this. My finger isn't rotating here. It's just slipping over the edge. That's what's been happening in connected particles all this time. You've never had to do any rotational energy or anything to do with rotation in kinetic particles, have you? Not even once. That means the pulleys aren't even spinning. They're just letting it slide over. Frictionless, theoretically frictionless pulleys. Okay? However, in this question, a fixed pulley is a disc of mass m and radius r, which is free to rotate without friction. Once again, a bit hypothetical there. How can you rotate without a bit of friction causing the rotation? Hypothetical. Okay? Then an axis through its center, perpendicular to its plane. What way is it rotating, guys? Put it in here. That's my plane, and it's rotating this way here. Everybody right with that? Now, once that's settled with, okay, there's only a weight on one side, isn't there? One end of a light inextensive string is attached to a point on the rim of the disc. Like a yo-yo, isn't it? Sort of like a yo-yo. Do you know where the yo-yo is connected at one point, and there's only one way it can rotate? And in theory, if you were to attach a weight onto a yo-yo and let the yo-yo spin, it could unravel the yo-yo. That's basically what this is. So, if I just rub out this side here, and we just imagine that the wire is wound around the pulley, and it's attached at a certain point. So what happens is when the weight is dropped, it spins this direction here, okay, as it drops. Now, what's the moment of inertia of the disc? It's a disc of mass m, radius r, spinning at its center. A half mr squared. Okay, a half mr squared. Okay, now that that's dealt with, going to do this is string is round the rim of the disc, and a particle of mass 2m hangs freely from the other end. So we're going to have a 2mg working downwards, and we're going to have t working upwards. The system is released from rest. Find the acceleration of the 2m mass and the tension in the string. Okie dokie. So what we're going to do here is Firstly, we have to find the speed of the 2m mass after it has fallen a distance h. Define h as the distance we're falling. Okay? So at the start of the question we're there, by the end of the question we're there. We used h amount of string. Okay, causing rotations. Next thing, gain in KE equals loss in PE. A half mv squared being the linear motion plus a half I omega squared equals, anybody? mgh. Now, we've got to be careful about that. First things first, when this spins, when we release the system, the potential energy gets transferred in two ways. What are the two ways it gets transferred? Into the linear motion, the linear kinetic energy of the fallen weight, or the rotational energy of the pulley. That's the two things that are going on. So this one is going to be the mass, 2m, and this one here is going to be the pulley. Is that right? So, let's start off. A half 2m times v squared plus a half, what do we say the I value was again? A half mr squared. Okay, we need a conversion rate for our omega again. Phi equals r omega, omega equals phi over r, phi squared all over r squared. How much does the pulley fall? We could define that as h, so it's 2m gh. Cancel m, cancel r squared with r squared, cancel m, cancel m. What we're going to have here is phi squared plus a quarter phi squared equals 2gh. Once that's completed, 5 over 4 phi squared equals 2gh. Isolate phi squared equals 8gh all over 5. Now, you might ask you, am I going to square root that? I'm going to break it down at all? Well, if you read the next part of the question, find the acceleration. We're going to have to use the whole phi squared equals u squared plus 2as again. The phi squared will substitute directly in as 2gh all over 5. What was our starting off velocity? The u squared? Huh? What'd you say? Was it 0? Yes, it was. Okay. So, it's 0. 2as, 2a times h. H is cancel. Bring the 2 underneath. Hg over 10 equals a. In my book, that's 4 over 5g. And we're close to being done. We have to get the tension now. So we go back up to the tension. I haven't even made a tension equation yet, have I? I just did conservation of energy. Haven't even touched the tension yet. So what we're going to have is T minus 2mg. Oh, wait, other way around, isn't it? Why am I leading with the weight? Going down. So 2mg going down minus T going upwards equals 2ma, that's also going downwards. Okay. Weight is bigger than tension. That explains the overall downward motion. Okay. Next thing after that is we are 2mg. T equals 2mg minus 2ma. 2mg minus 2m times the a. What did I say a was again? 4 over 5? 4 over 5g. 2 take away 0.8 is a 1.2. Maybe not. 2 mg minus 10, 4 over 5. Okay. Sorry? Yeah, it's 2 over 5, alright. Just put it into the calculator, ignore the mg, and you'll find out it's 2 over 5 mg. Okay, we're good with that? A disc of radius 2 meters has a circular hole of radius 1 meter removed from its center to form an annulus of mass m. Show that the moment of the annulus about an axis through its center, perpendicular to the plane, is 5 over 2. Now, technically speaking, I think if you were to just say a half m big R squared plus small r squared. Now, what does he have in his notes here? Yeah, he does actually reuse the formula. I'll have a look at the past papers. There is a case you might have to prove that from first principles, okay? Trying to take apart the language here. Show that as opposed to prove that. So there's an argument for just using the formula. Okay? So it's a half m times what's big R? 2 small r 1 5 over 2 m as predicted, alright? And this annulus is set up to roll from rest down a slope of incline 45 degrees. The annulus rolls without slipping. Find the linear acceleration of the annulus. So we set up our system, our wedge. Proper colours, that is. 1, 2, 3. And then there. There you go. There it is there, okay? Now, 2 meters to the outside edge and 1 meter to the inside edge. Okay. Anybody remember how to start these questions again? We've started the last 2 questions this way. Gain in KE equals loss in PE, conservation of energy. So gain in KE equals loss in PE. Okay. Gain in kinetic energy, once again, a half mv squared plus a half I omega squared equals mgh, where h is the loss in height of your object. Okay, how far does it say it goes down? Annulus rolls without slipping. Find the linear acceleration of the annulus. Does it tell me? It doesn't tell me how far it goes, so I'm going to need like a placeholder, like a variable. Just going to name it a letter. So I'm going to call it s. Okay. So s is defined as how far. S is defined as how far we're rolling down the hill. Is that right? How far we roll down the wedge. Therefore, s is at 45 degrees. S is the hypotenuse. That's 45 degrees right there. So it's going to be s over root 2 drop in height. Is that okay? S sine 45, s over root 2. Okay. So, what weight is the annulus again? It's of mass m. So it's going to be mg s over root 2. Okay, that part is done. Now we got to move over to a half mv squared. So a half mv squared, it's a annulus of mass m, so it's still a base that, plus a half. What do we replace in for I? I, anybody? 5 over 2m, or 5m over 2. For omega, so phi squared over r squared. Yeah, you can see there's a very generic build up to this question, very repetitive. It does come up. M r squared. Where is the other r squared? Oh, there isn't one this time. Ah, that brings me to my next point. R squared. Can we do anything about r? We know its value, don't we? It's 2, isn't it? So, no, it's 2 because 2 is the contact with the ground. It rotates around the radius of 2, while the inside one doesn't contact the ground, so it has to be 2. So that will make that 4. Okay, so we get gs over root 2 on the right hand side, and on the left hand side we're going to have a half v squared plus that 2 is still free, so it's going to be 5 v squared over 16. Okay, messy numbers here. That's going to be 13 v squared over 16 equals gs all over root 2. What am I being asked again? Find the linear acceleration. I have to find the a value. So isolate v squared and go to good old v squared equals u squared plus 2as. The a, which is the whole goal of the question, is just going to be a is going to be equal to v squared minus u squared all over 2 times s. If I isolate my v squared out of here, I can then just substitute it in without doing any further evaluation. V squared equals 16 gs all over 13 root 2. Insert directly into this formula here. A equals 16 gs all over 13 root 2. What's u squared? Big fat 0. Okay. All over 2 times s. Now, safe to say that the s's cancel. And that 2 multiplies by the 13, isn't it? So it'll be a equals 16g over 26 root 2. There's a g here somewhere. G. Half it's 8g over 13 root 2. That's it. Or the decimal version of said answer. Okay. Sorry? The 16 and the 26 were both it's okay. Shh. Okay. Where was I? Go back to the top. It's like, show that if mu is the coefficient of friction between the annulus and the slope, then mu has to be bigger than or equal to mu has to be bigger than, the coefficient of friction has to be bigger than 5 over 13. Okay, we don't want slipping, right? So look at this. Let's do some wedge work. Good old wedge work. Okay, we can ignore its size. Its size is almost irrelevant. But what we can say is that it's a mass. Its gravity goes directly down. How much does it weigh again? We're going for mg, aren't we? Weight as opposed to mass. We do what we've always done. What angle is wait. Parallel and perpendicular to the plane. What angle is that there? 45. Okay. So therefore, what does that make? There's a reaction force, isn't there? The reaction force R equals the component of weight going in the opposite direction. So what's the R value equal to? This here will be mg over root 2. Because you're it's not sinking in, like it's not like falling. How do I? Wait. Come here. Okay. It's not sinking in, is it? It's not going into the plane. It's going down the plane. means that it's balanced. Means that the R balances the mg over root 2. Okay? So, friction, so therefore your your friction value equals mu R. Okay? Now, friction works this way, against the motion. What acts in the opposite direction? It's also mg over root 2. Okay, where am I? Yep. Okay, so just gonna go down. Okay, so what we get here is this, guys. We have this driving us down the hill, which is our component of our weight, our mg root 2 that we spoke about earlier. What we have trying to keep us up the hill is the friction working against it, and we said that that's a mu R, which in turn is mu times mg over root 2. Okay? Now, please remember, that's your net force, isn't it? Your force, you're moving down the hill. Everybody agree with that? We're all moving down the hill. So your force equals your weight component acting that way minus the force of friction acting up this way here. Okay? And that's why on the other side we're going to have MA, because force equals MA, and that's why we're going to have M times the acceleration. The acceleration in the last question was 8g over 13 root 2. Now we're going to have to just quickly sort out the root 2's and the m's. Cancel. And then, what else are we going to have here? Sorry? Cross multiply the 13. Oh, the mg's. And then we're going to cross multiply the 13. 13 minus 13 mu equals 8. 13 mu is equal to 5 mu equals 5 over 13. Anything less than this, it's slipping. Anything more than this, it grips and it rolls. Does everybody understand? You can't afford to have a friction less than that. Otherwise it doesn't grip and roll. It starts sliding. Okay, so a mu value of bigger than 5 over 13. Okay.